Hi, my name is Ali Shirsavar and welcome to this Roden Short's Biricha Digital EMC filter design webinar. Over the next hour or so, we're going to talk about how you go about designing an EMC filter. We're going to do this in a step-by-step manner, and we're going to give you a design example with all the equations that is necessary, and then we will demo this, the performance of this filter using an RTM 3000. So, how much noise are we allowed to emit in order to make our product pass? Well, these are defined in standards. In particular, the important ones are EN 55022 or EN 55032, and the conducted emissions limits are defined here. Now, including at what frequencies. So in our case, we are really concerned about 150 kilohertz to 30 megahertz. And unfortunately, these are given in dB microvolts. So for example, the standard specifies that for a frequency range of 150 kilohertz to 150 kilohertz to 500 kilohertz, then you cannot emit anything more than 79 dB microvolts. It also specifies the method of measurements, quasi-peak or average. These are just the way it's been measured, which is also specified in the standard, and it's just a setting on your, let's say, spectrum analyzer or your oscilloscope. Now, the issue is that as electronic engineers, we like measuring harmonics in amps. These are currents, and therefore we have to measure them in amps. So for us as electronic engineers to design a filter, the first thing that we usually have to do is convert from dB microvolts to amps so that we can work out the equations. Thankfully, there's a very simple equation. So your current in amps is 1 microvolt times 10 to the power of voltage in dB microvolts divided by 20, all of it divided by 50 ohms. Now, we have pushed all of the equations that we discuss here in a spreadsheet, which will calculate everything for you, and this is what we provide in the workshop. So using this example, if the limit says 79 dB microvolts, that translates to 178 microamps. Now, if your power supply, let's say in the range of 150 kilohertz to 500 kilohertz, has a peak RMS or maximum RMS value of a harmonic more than 178 microamps, then you fail the test. And that is why you need to filter it. How do we calculate or determine exactly what is the peak of these RMS values? Well, the simplest and easiest way is to do an FFT. These days, simulators are extremely cheap, or many of them are free, and you don't even have to actually simulate the entire power supply. All you need to do is create a current source or a voltage source, in our case current source, and create this shape of your power supply and then just do an FFT on it. Okay? Now, if you don't wish to use or you cannot use the FFT, then there are some very simple equations. The reference is given here, which allows you to estimate these values. So if you do not have a simulator, then the RMS value of your first harmonic for a power supply with this input voltage, this output voltage, this efficiency, and this duty can be calculated from this equation. And again, we have pushed this into a spreadsheet that will calculate it very, very quickly. Okay, in this webinar, we're going to concentrate on DC-DC differential mode filter design, but the techniques that we talk can be applied to all the other types as well. So how do we force our noise to come below the line? Well, the most common method is to use an LC filter. And these are, again, equations that are straight out of a standard textbook. Your cutoff frequency or resonance frequency is given as 1 over 2 pi square root of LC, where L is here and C is here. I will talk about this damping capacitor and damping resistor in a little bit. Then another very important parameter is the Q of your filter. In other words, how much the gain is going to peak, because that's going to cause resonances. The Q equation is here. And then we need the output impedance. In other words, the impedance of the filter, when you look at it from this side, Z out, which is equal to square root of L over C in our case. And we need that for stability purposes and Middlebrook, which we are going to talk about a little bit later. So please note that often we use a two-cap circuit. This is one cap and two cap. I'm ignoring the the capacitor that sits here on the input called the pi cap, because it forms a pi filter. And the job of filtering is with this one, and the job of damping the Q is with that one. We're going to talk about that a little bit later. So often we have to also add an extra capacitor here. That's in order to form a pi filter. Let's call this C pi. Now that is used in order to attenuate the frequencies down the lower range, around 150 kilohertz or so, i.e. your switching frequency range instead of the harmonics. Now, during the workshop, we talk about this in great detail. Unfortunately, in this short webinar, we don't have time to do that. But what you should make sure is that C pi is either smaller than this or bigger than this. So you've got two ranges that you can play with. The L source here is the input impedance on this end, which will be the listen's input impedance. And L1 is the value that we calculate here. And switching frequency is FS. So we've got all the information that we need in order to size C pi. Now, also, although due to shortage of time we cannot discuss common mode filter design, the principles that we discuss here can be applied just as easily to common mode. It's just that your cutoff frequency is going to be different. So what we're going to work out here will just apply also to common mode filtering. Now, why do we use a two-cap filter? In other words, a capacitor there and a capacitor there, ignoring this C pi. It's because of the ringing that happens with a one-cap filter, like so. If you just had one cap here, sorry, I beg your pardon, one inductor here and one capacitor here. So the Q of this filter here is 1 over R square root of LC. Now, if, let's say, I design a filter with a cutoff frequency of around 7 kilohertz, if I set R equal to 0, so if I, let's say, use just ceramic capacitors here with very, very low ESR, you can see that with R set to 0, Q will be huge. And that would mean that you get massive peaking in the frequency response of this filter. And this will manifest itself as ringing, and worse still, it could cause instability because of Middlebrook stability criteria, which we're going to talk about a little bit later. If I made this R equals to square root of L over C, so if R is equal to the square root of L over C, you can see that Q will be 1. And of course, a Q of 1 means that it's slightly underdamped. And you can see here, R is set to 0. I've got massive amount of peaking. I've got 40 dBs of peaking in the gain plot of the filter. If I set the Q to 1, you would think that the peaking will disappear. It will, but look at what happens to the gain. The whole point of this filter is attenuate the noise. I like this 40 dB roll-off that I'm getting with this second order filter. If I use a one capacitor filter and I damp it, I damp to the Q here, I will lose my attenuation. This is much worse, as you can see, in terms of reducing my noise. So the solution is to use a two capacitor filter, and the job of this one and this one is to do the filtering, and the job of this one and this one is to do the damping. Now, provided that I make this 5 times bigger than that, then this will not have an impact on the cutoff frequency. However, it provides a path down here in order to allow some damping. Let's say here I start with keeping C1 constant, and I have got a CD, the damping capacitor, of 50 microfarads. And you can see that the peaking has already come down. If I increase that to 100 microfarads and keep everything the same, peaking comes down even more. If I make it 1000 microfarad, you can see that the peaking has disappeared. However, look at this attenuation. The attenuation stays exactly the same between this one, and this one. They're all going down at the rate of 40 dB per decade. And that is why we usually use this structure here. And of course, then we also add a tiny little capacitor here, which is the pi cap, in order to reduce the lower frequency noise. The reason we have to damp this peaking is because of Middlebrook's stability criteria. Now, in short, what Middlebrook says is that if you look at the impedance of your filter in this direction, it has to be much smaller than the impedance of the converter if you look at it in this direction, right? Otherwise, there will be an interaction between the filter and the control loop of the power supply, and you can get instability. So the conclusion is to make sure that our filter does not cause instability by making sure that the output impedance of this filter is at least 10 times smaller than the input impedance of this power supply. For example, if you calculate that Zin of this power supply, the input impedance of this power supply is 20 ohms, then Zout has to be around 2 ohms and not much more, otherwise you can have instability problems. How do we go about working out the input impedance and output impedance? Actually, it's really quite simple. You have two very simple equations, right? The output impedance Zout of this filter is square root of L over C, and that has to be a lot smaller than the input impedance of the power supply, which is the in squared times the efficiency of the power supply divided by the output power of the power supply. And of course, the reference for these equations is given down here. So if for our real-life design example, and that is what we're going to demo shortly, input voltage is 12 volts, output power is 6.6 watts, and efficiency is 85%, then the input impedance of the power supply based on this equation will be around 20 ohms. So the output impedance of my filter is going to have to be less than around 2 ohms. And you can immediately see that this is putting a constraint on the value of L and the value of C that I can select. Now we can very, very quickly visualize and design our filter graphically if we use an impedance paper. You've got many different equations, you've got many different constraints, and you cannot violate any of them. So the best way to do this is to actually draw it on a graph, draw all the lines that is above your limits and cross those areas out, and then you're just left with a tiny region of the graph, which is the L's and C's that you can use for your power supply that does not violate anything. That is done using a impedance paper. Please do not let this to intimidate you. It actually is very, very straightforward. It is just a very simple graphical way of calculating these two equations and working out these values. So as you can see with this graph paper, with this impedance paper, I can very quickly set my crossover frequency. Based on that, calculate the L's and C's, having crossed out all the regions of these capacitances and the inductances that I cannot use. So on the x-axis, I just have the frequency, and that is where you draw the line for your cutoff frequency of your filter. Then on the y-axis, I have the impedance of my passive component, right, in terms of ohms, which is this one when I design my filter. Then all the diagonal lines going down this way are the capacitances and how their impedance changes with frequency. So as you can imagine, this is, let's say, the line for a 100 microfarad capacitor. You can see that as the frequency goes up, this line is going down, which if you read it off this axis means that the impedance is going down. And of course, that is what you expect from a capacitor. Same applies to an inductor. I have got here the line for a 10 nanohenry inductor. We know that the impedance of the inductor goes up with frequency. So these diagonal line going up is the 10 nanohenry inductor, and its impedance versus the frequency. Now, based on this paper, I can very quickly design a filter, as we will do in the next slide. Let's say that we have calculated that our cutoff frequency for our filter, in order to pass the whatever standard, has to be 10 kilohertz. Actually, we're going to give you an equation for that very shortly. But for now, let us say the cutoff frequency of our filter is 10 kilohertz. So there we go. There we draw the line. Now, if you look at it immediately, you can see from this graph that you can have any value from 10 millifarad and 35 nanohenries to 7 millihenries and 35 nanofarads. Now, it is unrealistic to be designing a filter with this huge range. So let us now just go back a few minutes and think of things that we do know that constrains us from being able to select certain component values and cross those out on the graph paper. For example, let us assume that you cannot physically buy an inductor smaller than 100 nanohenries. So this is a 100 nanohenry line, and anything smaller than that, let's say you can't buy. There we go. You cross that bit out. So immediately you're making your range smaller. So then we know from Middlebrook that there is a upper maximum to the impedance, the Z out of the filter. For simplicity, let's say that is 1 ohms. You draw the 1 ohm line right here, and you know that the filter that you design cannot have an output impedance above this line. So you just cross all of that out. Then let's say for DC bias, size, cost, for whatever reason, your capacitance cannot be more than 100 microfarad. You draw that line, and then you know that anything above 100 microfarad has to be crossed out. So suddenly, going from this massive range of 7 millifarad and so on, we narrow it down to this tiny area over here, which is the values that we can use that does not violate our other design constraints. So that means that we can have a capacitance between 20 to 100 microfarads and an inductance between 3 microhenries to 20 microhenries. So that is now a perfectly reasonable range of component values that you can use in order to design your filter. Okay? Now, in the previous example, we said that we are going to have a cutoff frequency of 10 kilohertz. Where did that come from? Let us assume that for the workshop converter, or the one that I'm going to shortly demo for you, our switching frequency is 200 kilohertz, and at 200 kilohertz, the RMS value for the 200 kilohertz harmonic component is 750 milliamps, right? Let us also assume that we are going to have to attenuate this from 750 milliamps down to 1 milliamps, just for simplicity, just of the example, in order to pass whatever standard. Now, we know from university textbooks that the gain of a second order filter at a certain frequency is amplitude after filtering divided by amplitude before filtering, the square root. So in my case, at 200 kilohertz, which is my switching frequency and my biggest harmonic, I want to go, I have 750 milliamps, I'm going to attenuate it down to 1 milliamp, therefore the gain is going to be this value here. Okay? Okay, I haven't got my cutoff frequency yet, but I know what the gain of my filter at 200 kilohertz should be. Then, again, from university days, we know that the gain of a filter is cutoff frequency divided by the frequency at which we are operating. So, if I know that the gain at 200 kilohertz is 0.0365, then cutoff frequency that would give me that attenuation or that gain would be based on this equation around, around 7 kilohertz. Also, please note that in many application notes or data sheets or filter design book, they talk about current attenuation or insertion loss. These are just the reciprocal of gain, with insertion loss usually being specified in dBs. It's just a different way of representing almost the same number. So it all depends on whatever you're more comfortable using. So if you're more comfortable using insertion loss, that is perfectly fine. For the purpose of this webinar, we're going to use gain of the filter because many electronic engineers have used gain all the time, and effectively that is what we're going to use in order to do our calculation. So now we know everything to design a real filter. So let's design one. We start with our specification. From the specification of the previous slides, we know that we need a cutoff frequency of 7 kilohertz in order to attenuate 750 milliamps down to 1 milliamps. We also know from the specification of our power supply with the input voltage, efficiency, and output power, etc., that its Zin was 20 ohms, and therefore, because of Middlebrook, Z out cannot be bigger than 2 ohms. We can immediately draw these lines on our impedance paper. So first, this is the 7 kilohertz line. Okay, so that is the cutoff frequency. I already know that. I also know that Z cannot be more than 2 ohms. Okay, that's because I'm Middlebrook. So I can immediately cross all of this area and all of this area out. Okay, then the intersection between this line here and that line here immediately gives me the minimum value of the capacitance and the maximum value of the inductance that I can use, because that is the absolute minimum value. Otherwise, any lower, I will violate the Middlebrook stability criteria. So the minimum value of my capacitance cannot be less than 10 microfarads. And at the same time, the maximum value of my inductance cannot be more than 50 microhenries. Okay? So I've immediately limited. I'm already limited because of Middlebrook and because of this cutoff frequency. Then let us assume that our bulk or damping capacitor is already soldered on the power supply. This is actually often the case because when you design the power supply, the bulk capacitor on the input is specified as a result of ripple requirements of the power supply. So you find yourself that you've already got a couple of 100 microfarads worth of electrolytics already soldered onto the input of the power supply even before filtering. So let's say that the power supply designer has already soldered a 500 microfarad capacitor due to a ripple requirement. Now this will set the maximum value of the capacitance because we said earlier on that the bulk capacitor or the damping capacitor has to be 5 times bigger than the filtering capacitor. So there we go. If my bulk capacitor on the power supply is 500 microfarads, and I'm going to use this as a damping capacitor, then 5 times smaller than that is around 100 microfarads, and that is the maximum value of the capacitance that I can use. Okay? Then as this reaches my cutoff frequency line, it determines the minimum value of the inductance. So the minimum value of the inductance I can use is 5 microhenries. So I end up with a small range between these two limits. Now, these are perfectly reasonable limits from the massive expanse of component values that we initially had. We have our LC range, but ideally, we want to use the internal ESR of the damping capacitor in order to damp the Q so that we don't have to solder an extra resistor in series with the damping capacitor. Okay, so if CD is known, in our case 500 microfarads soldered on the board, then you also know its ESR. In our case, it's around 200 milliohms. I know that because I have measured it. So let's see what the Q is going to be. If I use the range on top here, which is 50 microhenries and 10 microfarads, then from my equation, I need a damping of 2.2 ohms. Okay? That would mean that I would have to add an extra resistor in series with my damping capacitor. If I use this here, value here, which is 5 microhenries and 100 microfarads, the damping resistor is 220 milliohms, which happens to be very close to what I have internally as the ESR of my capacitor. So if I use 5 microhenries for my L of my filter and 100 microfarads for my C of my filter, then I meet the criteria, plus I don't need a damping resistor. Okay? I can read off the impedance off from this axis to give me a Q of 1. There we go. So our filter is actually complete now because we have worked out L, we have worked out C, we have worked out CD, and we have worked out RD. So a final summary, we started with simulating or estimating the magnitude of our largest current harmonic. Then we said that it was 750 milliamps at 200 kilohertz. Our specification asked us to reduce this to 100 milliamps. Based on this, we calculated the cutoff frequency to be around 7 kilohertz, okay, for a second order filter. Then we knew that we had 500 microfarads on the power supply already, and it had the ESR of 22 milliohms. There we go. I've just put them on. And we limited the L and C choices based on our constraint on the impedance paper. And we had this range here, okay? Now, a good choice, therefore, would be around 4.7 microhenries and 100 microfarads of parallel ceramic or aluminium polymer capacitors in order to meet all my criteria. So there we go. I've got 4.7 there, about 100 there. And then we check to make sure that the Q is not too large. Q of 1 would be ideal. You could possibly get away with a Q of around 4, but if you get to that, you really should measure the loop and make sure that the loop does not dip around the resonance of your filter, because then that would show that there's an interaction between the filter and the power supply. Okay, the ESR was already around 220 milliohms, so we had a Q of around 1. That was good. And our design is complete. So what I'm going to do now is I'm going to demonstrate for you how we calculated these numbers and how we're going to measure them. Okay, so this is the spreadsheet that we provide to the engineers in the workshop. There is one for DC-DC EMC filter design, and there is one for AC-DC. Now, there is a phenomenal amount of equations and design guys that has actually gone into the spreadsheet. You've got many tabs, and each one does a different thing. On the first tab, we have got various limit lines for the standard that we're using in the class. And then you've got a unit converter whereby you can easily convert, for example, from dB microvolt world into milliamps and so on. But the one that I'm most interested in is this one. It's the filter designer. Now, if you remember, we gave all the equations in the presentation, but here I can actually type these in, and the spreadsheet will automatically calculate those equations that we provided. It does both differential mode filter and common mode filters. Unfortunately, we didn't have time to go through common mode filtering in this webinar, but the principle actually stays exactly the same. Now, if you recall, the power supply that we designed in the class was 12 volts, and this is the one that we're going to demo for you. 6.6 watts. Let's say the efficiency was around 85%, and you can see immediately that it has calculated for us the input impedance of the power supply at 18 ohms. We approximated to 20 ohms in the presentation, and it's also calculated the Z out of the filter at its maximum value. In other words, what is the maximum Z out that we can tolerate, which is 10 times less than that. It says 1.85. In the actual design example, we use 2 ohms. Then the switching frequency of this power supply is 200 kilohertz. Yeah, and the frequency of the first harmonic of this power supply that falls in the test band is also 200 kilohertz. And which number of harmonic it is the first one, so that remains at 1. And let's say that the duty is around 35%. So now here, the spreadsheet automatically calculates the estimate of the peak RMS value, the maximum RMS value of this 200 kilohertz component at 740 milliamps. And when I simulated it, I got 760 milliamps. So you can see that the equation that we presented in the class, in the webinar, is actually quite accurate. So then we go to the next tab, which is the EMC filter cutoff frequency calculator. Again, if you remember, the next thing that we did when we calculated this maximum value of our first harmonic was to go and calculate the cutoff frequency. These values have already been filled in from the previous tab, so 200 kilohertz and 760 milliamps. And we said that we wanted to attenuate 760 down to 1 milliamps. And as soon as I type 1 milliamps into there, the cutoff frequency gets calculated. If I change it to 2 milliamps, you can see that the cutoff frequency also changes. So back to 1 milliamps, which is the one that we did in the presentation and the one that I'm going to demo. It has calculated the gain, just like we calculated with the equation in the presentation. It has also calculated the attenuation or insertion loss if you are more comfortable using insertion loss. And here, the cutoff frequency is 7.3 kilohertz, and of course we calculated it to be around 7 kilohertz, which is the one that we used on the Z out, sorry, I beg your pardon, on the impedance paper. There are a lot more tabs here, including a pi filter calculator. Again, unfortunately, we did not have time to go through the details. The principle is very similar. I've given you the two equations that you need, which is the most important two equations that limits the value of the pi filter. But again, this tab will calculate everything for you on this spreadsheet. So let us now go to the experimental setup, whereby we are going to have a look at how this filter that we have designed performs in real life. Okay, so here is the lab setup, very similar to what we have in the class. This is the buck converter that we designed earlier on, the 12 volt in, 3.3 volt out, 6.6 watts. This is the one that we use in some of our classes. In the actual filter design class, we also design for isolated and non-isolated power supplies, and we even design an AC line filter for PFC. Starting with the specification that we discussed in the presentation, I've got 12 volts input voltage coming in. It's going through the listen, and then from the listen, it's going to the power supply. At the moment, it is not filtered, and I have set the Rode RTM 3004 scope in order to display the harmonics for me. So the range right now, it's from around 50 kilohertz to 5 megahertz, and you can see these spikes. I've set the resolution bandwidth to around 9 kilohertz, just like the standard requires. I'll talk about these a little bit later, but for now, out of the listen, the harmonics is going into the Rode Shorts RTM 3000, and I am seeing these values. Now, I can have a look with my cursors, and there we go. I go peak next. That is the second harmonic that is finding for me. And if I grab hold of this one and I go next peak, there we go. Now I'm having a look at the amplitude of these first two harmonics down here. This is the first harmonic at 200 kilohertz, and it's 85 dB microvolts. And this is the second harmonic at 400 kilohertz at 80 dB microvolts. Now, this is before filtering. Then in the class, we designed several filters. So this is the filter that we actually designed in the presentation. And what I'm going to do is I'm going to insert that between the input power, the 12 volts, and the power supply. And I'd like you to have a look at how this filter will attenuate all of these harmonics. Okay, so I'm going to remove the power. I'm going to convert it to the filter, and I'm going to turn the power back on. And you will see that almost all of the high-frequency components have pretty much disappeared. There is still some low-frequency components down here. We'll talk about that a little bit later. But for now, you can see that the filter that we designed has completely attenuated all the high frequencies. I can increase the stop frequency to 30 megahertz, which is what the standard requires. And you'll see that it is very, very low. You still see some spikes around here. It's very, very low. It starts to creep up around here, and that's because of some common mode noise getting in. Obviously, at high frequencies, we've got more and more common mode noise. This is only a differential mode filter, but as I mentioned earlier, the principles that we discussed applies pretty much to the other types of filter also. So let's take the stop frequency back down to around 5 megahertz. And you can see here, after filtering, you've got these spikes, but everything else disappeared. Now, for comparison purposes, what I'm going to do is I'm going to save that into one of my references. So I go here. My source is a spectrum. I'm going to copy it into reference 1. There we go. The white line now is the harmonics after filtering. So I now can remove this, and I can add now. There we go. So what you see here is the harmonics before filtering. the red lines, red and orange line, and the white line is after filtering. So you can see how much this one filter has attenuated our noise. However, one thing to point out is that the lower frequency components have not, they have attenuated, but not as much as you'd expect them to. There are many reasons for that. First of all, let me get rid of the reference so that we can see it better. There we go. There are many reasons for that. One of them is, of course, that this is not an ideal setup. My ground plane is not nicely coupled. The ground plane of the listen is again not nicely coupled. Now, in a real setup, on a real power supply, this will be integrated into the power supply. I've got dangly wires between the filter and the power supply. This is for teaching purposes and how you go about designing filters. But of course, when it comes to become a product, all of these will be soldered on board of this converter. The other thing is that if you remember earlier on, we said that often we need to put a pi filter cap, so a C pi, right on the input. That attenuates lower frequency components around the switching frequency. In my case, that is 200 kilohertz. So let me reduce the stop frequency to, let's say, 1 megahertz. There we go. These are now the peaks that are not being attenuated with this filter, but I don't have a pi cap at the moment. What we do in the class is that we add a pi cap manually in a real converter or a filter. This will be soldered on the board, but you'll see the impact in a minute. So first, let me look at the peaks after filtering. So I go to my cursor, next peak. There we go. And that is at 200 kilohertz. After filtering, it has gone down from 80-something dB microvolts down to 75 dB microvolts, but that's still too high for me. I want to have it a bit lower. And for my second harmonic, again, let me get it to find the peak. There we go. For the second harmonic at around 400 kilohertz, it's down to 61 dB microvolt. Now, have a look at what happens when I add this pi cap onto the input. So there we go. It jumps down from 75 down to 62. Now that is a massive jump. That is over 10 dBs from 75 down to 62. And of course, as I said, with correct layout and tying it nicely to the chassis, this power supply would be absolutely beautiful. Now we can have a look at the complete range. So I'm going to go stop at 30 megahertz, including the pi cap. And this is the spectrum that we have. Note that here it's 28 dB microvolts. So the whole power supply, including filter, is performing extremely well based on everything that we designed. So let us go back to our presentation. If you remember earlier, I said that we will provide you with all the equations at the end. All of these equations are already embedded within the presentation, but I have put them all on this slide to summarize everything. So the first thing that we did for our power supply was to estimate the amplitude of the harmonic that we wanted to attenuate. We used this equation or simulation. And we, in our case, the switching frequency was 200 kilohertz and the amplitude was 750 milliamps. After that, we wanted to work out the cutoff frequency of the filter. And in order to do that, we used this equation. So we knew that the amplitude before filtering was 750 milliamps. And we picked an arbitrary number of 1 milliamps just for calculation purposes, which would be our desired amplitude after filtering. Given that this harmonic is occurring at this frequency of 200 kilohertz, then we calculated this cutoff frequency of the filter to be around 7 kilohertz. So then we had a bunch of other equations which are given around here. I mean, that is the standard equation for working out the cutoff frequency, which is 1/2 pi square root of LC. But we said that unless we limit our choices because of our constraints, you have effectively a huge choice. At that point, we used an impedance paper, and we used various constraints. In particular, for using the Middlebrook stability criteria, we were limited with the Z out of our filter, and we calculated again all of these. We drew it on the impedance paper, we drew the lines, we crossed the regions out, and we homed in on the values of L1 and C1, and of course the damping capacitor and damping resistor. And here's the equation for the damping capacitor. And to set the Q to 1, here is the equation for the damping resistor. And finally, we talked about a little bit about the pi cap, which is the capacitor that sits here, C pi. We didn't have enough time to go through it in a lot of detail, but we just provided you with two equations that you must not violate in order to calculate the value of C pi. L source here is the inductance or the impedance of your listen. L1 is this value there, and Fs is the switching frequency. And therefore, you can see that we can calculate down to component level all of these values. Then we showed you a spreadsheet whereby all of these equations were already embedded in it. And then finally, we showed you some really nice experimental results using the workshop power supply and the filter, and using the Rohde & Schwarz RTM 3000 oscilloscope. So some concluding remarks now. I hope that you enjoyed this presentation. Although due to the shortage of time, we did not manage to cover common mode filter design. The techniques that we covered here are applicable to this type of filter also. For a downloadable version of the impedance paper and much more, including automated power supply design software and PFC design software and so on, please visit www.biricha.com/2020. This is the end of my section of this webinar. I hope you enjoyed it. Thank you very much for watching, and I hope to see you at one of our workshops.